Cool. So first, thank you very much for having me, for having us here today. We're very excited to speak about our newest paper, which we are currently writing, which is published on RWTH, but currently is going through journal review, which is about fast columnar physics analyses of terabyte-scale LHC data on a cache-aware Dask cluster. So quite a lengthy title. But we will get through it step by step, of course. And also, I'm giving a little bit of a teaser now because we've also prepared a little live demo today, such that you can see the Dask cluster really. So this is work we've been preparing with Niklas Eich, Martin Erdmann, Peter Fackeldey, Benjamin Fischer, me, and Yannick Rath, many of whom, as you can see in the participant list, are here, of course, as well. So let me start with a motivation why we do what we do. So what is our motivation to go fast on a small size computing cluster? So usually when we're doing high energy physics analyses, you know, we have data in the order of terabytes, can be 10 terabytes, 100 terabytes, totally depends on what you want to do. And then you write your analysis code, usually either C++ or Python code or something, to extract from this data in the order of terabytes and scientific output, which is in the order of kilobytes, all right here. So the final PDF, the final plots, so the final scientific message, which is really, really dense. And really crucial is that the small time to insight of this analysis really drives the high physics potential of the analysis. Because first, of course, you can tune existing methods. For example, if you have a cut in your analysis, or if you have an MBA method or something, when you can go fast from input to output and see really fast what the scientific output of this new method is, you can tune it particularly well. And of course, also you want to investigate new methods. We're physicists and we're trying out many well-motivated things. And doing this fast, of course, is nice because you can try many different things. Our ultimate goal, so to say, is that we have an analysis in the duration of a coffee break. So 15 to 20 minutes would be perfect, such that it synchronizes with the thought process of the physicist. And not only for a very fast and a very nice analysis, this is very crucial, but also when we're looking a few years ahead, for example, to high Lumi LHC, then the data amount is just so high that we need really the best methods and the fastest methods to extract the scientific output still as good as possible. Our physics analyses we do here in our cluster. So I would say we are standard CMS institute. We have about 9 people working on CMS analyses here. We have 1 professor, which is the supervisor of our group. Then we have 3 PhD students working in Higgs pair production. One of them is me, 2 people working in Higgs Strahlungsprocesses, so investigation of this BH coupling. And then we have various other methods investigated by 1 PhD and 2 master students. So for example, investigating new MBA methods, studying jet flavor tagging, or different smaller studies. And all these analyses and all these people have very common challenges, as you find out. We all have very many inputs. So for example, we have the simulations on the one side and the reported data on the other side, which are really terabyte scale data sets. So really big. And also we have metadata. So for example, efficiency scale factors, which are measured, corrections, which are measured by other groups, and so on. Then we're all doing heavy computations. For example, you have an event reconstruction where you need to extract an invariant mass of a dilepton system or something like this, or you need iterative algorithms and so on, or you need MBA algorithms. So very heavy computations on the other side. And of course, we want to have a very good scientific practice. So of course, we need a good bookkeeping to know what we are doing and still know it after half a year, 1 year, many years. And this investigation that we all have the common challenges led us to the thought that we really should have a shared software repository. And this shared software repository is where all this is implemented, and all what I'm going to show you today is implemented as well. You can click the link and check it out if you want. So our analysis strategy, our analysis structure is usually that we have two types of different inputs. So on the one side, we have event data, where all the scientific physics events are stored from the collider, from CMS experiment in this study here. And also we have these metadata samples. And then we have in the order of 100 different computing steps. So for example, we have the preparation of the metadata, we have the pre-processing of the whole event data, then we have the main processing of the whole event data to really extract in the end histograms, plots, everything you might want to see, everything you might want to check, not only during the final publication, but also, of course, in a physics analysis, in the mean steps, in the meantime. And all these different tasks, so I said in the order of 100, they're connected using the Luigi analysis workflow, which is abbreviated by LAW. So you can also click the link, software package, which is based on Luigi, which was originally written by Spotify and then open source. And it's really nice systems to stitch together all these different tasks to really have one analysis graph, so one analysis flow where the data is flowing. And our typical workflows in the analysis are, for example, we want to do a full analysis, which is what you need in the end. So all different corrections, all different systematic uncertainties and everything goes in there, and then you get out the final result. But also, of course, during the development of the analysis, you want to develop one of the order of 100 different tasks, tune it or have some different method in it or something like this. And there you need the repeated evaluation of, for example, one of the pre-processing steps. Also, of course, you need good debugging. So if you are, for example, see that one of the tasks in the analysis chain is failing, you want to investigate why is it failing and find out what is wrong there. So also there have the repeated evaluation of the single tasks. And one other typical workflow would be that your supervisor goes into your office and says, okay, show me this plot from this and this feature in the detector. And then, of course, you want to go very fast from the initial event data to this plot your supervisor or yourself, of course, want to see. And how LAW stitches all these tasks together is then in the make-like execution system. So you have this really make-like execution of the whole analysis. For example, in our case, you would just in the end have one command line command, which is LAW run full analysis. And this then builds this task tree here. And this is just really a small excerpt from one of our DAX analyses. And we can see on the top, we have one task, which is called here, not full analysis, but it's called AN 2119, which is the technical name of our pre-publication analysis node. And this task then really requires all the different plots, which will be in the final PDF in the end. And all these plots require the succeeded processing of the data, which boils down to the initial processing of the event data. And this task graph can then be visually represented in a tool called the Luigi Scheduler, so developed by Luigi, and we can use this for the overview, to get the run status, to see the structure of the graph, make structural improvements, and of course also for debugging. Then when we go through our initial sketch here, so I said, first we start with the inputs. On one side, we have the event data, which is in the order of 10 to 100 terabyte. So we have the recorded data and the simulation. And what we're using here is a file format, which is very small. So we have just 1 kilobyte per event, which is called the nano AOD format. And also inside our analysis, there goes the metadata, and the metadata is usually in the order of megabytes. So we have efficiency measurements, like I said, scaling factors, which are usually saved in, some kind of Wiki pages, JSON files you get from your colleague, custom root files, which are based somewhere on the CERN servers and so on. And then we have on the one side the preparation task, so to prepare this information for the main processor, for example, download the files, change the formats. For example, you have a trigger efficiency, which you would like to convert from a root to a coffee histogram or something like this. And also we have these preprocessors, and the preprocessors are really a little bit different because the preprocessors are pre-structuring the data and already need to read the event data. For example, you would need to count the pileup distribution in advance to processing. And these preprocessors are very read intensive and they are repetitively going over the data. Then the next step is the processing, so the main processing, which is done in the preprocessors and the processors. And this is now done via a map reduce scheme, and the processor maps, which I said, are really performing the real computing payload. They are very fast in our sense because we use a vectorized processing, which is based on Awkward and NumPy. I'm sure you are very well aware of. And for example, if we have an MVA evaluation task, we use a central GPU server instance that all these different map instances can communicate with. So we have our data in the beginning, which contains all our events, which are grouped in two levels of hierarchy. So first, they are grouped by the data set, which would be the physics data set, for example, TT bar, single top process, Drell-Yan process. And these data sets are then divided into chunks, which keep 100,000 events each. And each of these chunks is then mapped onto one of these processor map instances. And in the second step, of course, we have to merge these objects which come out of the map processes, which can be histograms, event counts, cut flow statistics, and so on. And this reduce step then takes all the outputs of the maps and just merges them basically. Histograms here are a pretty special case because compared to only event counts or cut flow statistics, these histograms can be quite large. So of course, first they can be multidimensional, have very many dimensions, like for example, systematic uncertainties could be one dimension, or the data set could be one dimension, the process could be one dimension, and the feature could be one dimension, and so on. So they could be multidimensional and of course also very large, so in the order of gigabytes here. And for this, we implemented pretty fast histogramming methods, which you can access if you click this thing here, which is basically an implementation of the hist library based on the H5Py backend. And they can efficiently perform operations like expand, so expanding your histogram, merging two histograms, or compress a histogram such that it gets compressed representation. And then we use, like I said, this map reduce scheme. So these maps can now be parallelized over with multiple worker nodes in our cluster, going through all these different chunks. And in our case, we have a small HPC cluster. So we have a portal node where we log in and start the user session, and we have a worker pool. What exactly this worker pool is representing, you will see in a minute. And then we start a two-step process. So first we spawn HT Condor jobs on the worker pool, each HT Condor job using one CPU thread and about 1.5 gigabytes of RAM. And in the second, we use Dask to start Dask jobs in these HT Condor slots. And then in these HT Condor slots, the jobs are run and they do their main payload. And then, of course, we need to reduce all this. So what comes out of the Dask, these parallel Dask jobs, for example, histograms, or like I said, cut flow statistics, and so on. And for this, we start 10 parallel reducers on the portal node. So I just draw here 2. And they just run on the portal node and have are only limited by the RAM capacity of the portal node. And then each reducer has 2 reducing instances, and they are reducing the output of the Dask jobs. So they have a normal reduce in case that one of the Dask jobs, in case one of the map jobs finished regularly, then they just reduce by pulling the job from the output from the Dask job, or they have an early reduced instance. So if the Dask job sees, okay, I'm close to the 1.5 gigabyte RAM that I have, and I need to lose some of my data, then the map job can push its data to the reducer instance as well. On the software side, everything that I showed you, everything that I will show you is implemented in Python. So I just put here shortly before the talk the GitLab depiction, and we can see it's like 98% Python and a little bit HTML or something for plotting. In our analysis repository, and we're using a modular software framework. So we use all these standard tools like NumPy, Matplotlib, Dask, HTCondor, and of course you're very aware with the HEP specific tools, for example, awkward array, uproot, MPL-HEP, and Coffee. And by having all these very nice modular software frameworks, this is very, very stable on the one side, and of course also very modular, so you can exchange different parts as well. The resource we're using is our local institute cluster, and this institute cluster is really pretty small, but enough for our group. So we have optimized it for scientific data analysis and machine learning. And on the hardware side, you can see, okay, we have first enter from the internet, let's say with a 10 gigabit connection onto our switch, and on the switch then we have different different nodes. So for example, storage, which has 120 terabytes of HDD storage and 2 terabytes of SD storage. Then we have the portal node, the node you would usually log onto, which has 64 threads. And then we have different instances of worker nodes totaling to about 224 threads, so CPU threads, about 832 gigabytes of RAM. And because our cluster is also tailored to machine learning applications, we have 17 different GPUs on the various workers. So this was our hardware setup. And on the software side, we have the system software, which is just an Ubuntu OS with some additional packages, which is distributed via Ansible. So Ansible is a very nice tool where you can just basically code the state of the cluster, and the state is then transferred onto the cluster. And we have the analysis software. So the packages I just showed you, Coffee, awkward array, and so on. This is installed via Conda and then shared just over the network from the storage. And also our user base is not only consisting of the researchers at the institute. So we have the CMS experiment on one side, and also we have the Auger Observatory group, which is investigating data from the Auger Observatory on the other side. And these are about 10 researchers which use this cluster on a daily basis. But additionally, we have courses which use this cluster, for example, for nuclear physics or machine learning in physics and so on, where we have about up to 200 participants using this cluster for either physics applications or deep learning in physics applications and so on. And also we host schools and workshops on this cluster, particularly in machine learning. And this is why we have developed the front end for data analysis, which you can open in your web browser. So a student would just click a link, make an account, and then he or she can use the interface with a little IDE and execution editor in the web browser. So, and what I just showed you, I would like to show you in the real world. And this is the reason why my colleague Niklas is here with me. And now I want to try if this works. So Niklas will turn on his camera, and I think you can see it. And because I'm speaking still, I think Zoom puts the focus on my screen. So maybe you can just fix the camera from Niklas. So hi, here I am. And now we're taking a little tour to our server room because we're just sitting in the room besides it. And then we can open the door here. And this is really now the server room of our institute, where we have different machines from the different experiments and so on. And what you can see here is the Whisper cluster. So we make a little tour. What I just showed you in the slide really, of course, manifests itself here in the hardware. So the first thing I showed you was the Whisper switch. And this is the Whisper switch. You can see here all the cables going in and coming out the way you see it. Here are two black cables, and these two black cables are really the connections which have the most power. So these are the 10 gigabit connections, one for the outside and one for the network storage. Then we have here various management interfaces for all the machines. And then you can see here the green cables. The green cables are connected to the small worker nodes, and here the blue cables are connected to the medium and the large worker nodes. And these I want to show you in a second. First, we have the Portal node. The Portal node is here. It's one of our strongest machines because every user needs to access it and need to be on it. And then here we have the different storage. So here we have the different HDDs, and inside the machines are also the SSDs. And now we come to the worker nodes. So here we have these 10 machines. I told you we had 4 of these small workers, but really we have 10 of these small workers, but only used due to the for this benchmark. I will show you 4. So these are here now all 10. We will open one in a second. And also here are the medium workers, worker 2 and worker 3, and we have the large worker, which is our most powerful machine here. So now, as I said, we want to open one, and we are going to open here one of the small worker machines and take a look inside. And I guess the most of you have seen this. Just looks like a normal workstation, which is mounted in a rack. So we have here the CPU with the fan, of course, and here the 2 GPUs, and one very crucial part which we will use in the future of this talk is the SSD, which is mounted here. So 1 terabyte SSD, which is connected via a SATA port just here. So this was our small tour through our cluster. Let me get this back, and then we'll get back to the slides. Unless you have questions now. That does not seem to be the case. Okay, very good. Okay, so then thank you very much, Niklas. We'll get back to the slides, okay, you can see the slides again, right? Or still? Yes, looks good. Okay, so that was our live demo. Now, by all this processing, so we have seen that the data is streamed from the central network storage, which you just saw, to the worker nodes. And now on the worker nodes, we have these map jobs. And these map jobs are now really very, very time efficient. So they are very, very fast using this vectorized processing via NumPy and Awkward. So we identified a very new bottleneck for us. And this new bottleneck was that the central network storage has 2 limitations. So first, we have this network storage is based on the HDDs. The HDDs have 120 terabytes, but of course they have a very limited read speed. And additionally, the storage is connected with 10 gig to the switch, and then with 1 gig to the small workers and 4 gig to the medium and large workers, as you've just seen. And the streaming of the data then really becomes the critical bottleneck. And we can see this in our data. For example, if you look here in our Grafana interface, I've brought 3 different plots. So one is the network I/O, so how much data is streamed onto the machine. The second one is the CPU wait, so how long has the how much of the percentage does the CPU have to wait for something else in the system? And the third is the effective CPU usage, so how much of the CPU is used by the user's process. And you can see that in this region here is very calm, and then due to this triggered behavior, from this point on, the job needs more data. So the job has finished processing all the data it had on the storage elements, and then the job needs more data. And of course, the machine has to pull this data, so the network I/O rises, and the CPU wait also rises. And what this then effectively happens is that the effective CPU usage goes down from about 60% here to about 30% here. So you have this 50% in speed loss, which is really, of course, not very nice. And we try to overcome this, and this is what I'm going to show you in the last third of the talk. So we've seen that our critical bottleneck is really the streaming of the data to the processing elements. And we thought about, okay, what are our options? And we saw that we have various storage types and locations available to solve the problem. First, we have the WLCG. This is where originally our data is stored. This is where originally our data comes from. So we have an order of petabyte storage in the WLCG, and we have a speed of about 100 megabytes per second in the order of. We have also many users, so many competing users in terms of access. And we have sometimes observed a very high latency to reach this data. Then from the WLCG, the data enters our net attached storage, and this net attached storage has a size of about this 100 in the order of 100 terabytes, and also the same read speed, because also HDDs. There we can store the experiment data for our group. So by storing the data on the storage, we do not need to access it from the WLCG all the time. And then we have all our different worker nodes. I only depict here one. And in the worker nodes, as you've just seen, we have this SSD in the order of 1 terabyte, which can be read with a speed of 500 megabytes per second. And also we have, of course, the RAM, where it would be nice to have stored all our data in the RAM, but unfortunately it's only the size of about 10 to 100 gigabytes, but of course very fast with a speed of 100 gigabyte per second. And then in the last instance, of course, you also have the CPU with the L1, L2, L3 cache in the order of megabytes really only, but this is of course, as you know, heavily used by things like NumPy and SIMD processing in general. And this worker then needs only the fraction of the data which is processed by this worker. And now in the next slide 18, I'm going to show you this network storage here, and slide 19 to 21, the worker storage. So the network attached storage is really there to save our experiment data on site. We have very easy and reliable access, so no timeouts, no unforeseen timeouts, and we do not need any specific credentials for it or something. And of course, it has a very direct connection to the worker node, so low latency. And in principle, the whole NFS, the whole network attached storage can be accessed with 10 gigabit. Inside the network attached storage, we have 3 storage tiers. So we have the /home, which is about 2 terabyte, where all the user homes are stored. And they are backed up by the local computing authority every day. Then we have this Scratch data space with 24 terabytes, which is used for mirrored experiment data. So data from your experiment you really do not want to lose. And we have the /store, which we will talk further about in the coming time. which is for unmirrored experiment data. So experiment data that could be retrieved from the WLCG, for example. And this /store is stored in a RAID 0 storage system striped across 6 different 16 terabyte HDDs. And what this means is, for example, I depicted here for 3 disks, you have 3 disks, and the storage blocks are then striped. So that means that first, the one file, for example, I depict here in a little bit darker gray. One file may be stored along block 1, block 2, block 3, and the block 4 here. So the HDDs can be read in parallel. So this enables then faster reading by a factor of 6 if all the HDDs are read in parallel. So this is the first improvement. And the second improvement, now we're here on the worker nodes. And on the worker nodes, we want to use this SSD to minimize really the network traffic throughout our cluster. And to use software implementation that we use there is FS cache and cache files, the cache files daemon. And this really enables a transparent caching, which is already available in the Linux kernel. It has a granularity on the block level, so 4 kilobyte, which is very nice for us. And the strategy is the least recently used strategy. So how this works is that we have the NFS, our network storage, and this NFS streams the data to the NFS client, and the NFS client then streams it forward to the virtual file system, so the file system you would like to use, and this then gives it to your user application. But at the same time, the NFS client, if he sees that this data is not cached yet, speaks with the FS cache, and this FS cache speaks with the cache files over the cache files daemon and stores it into the backend of the cache. And now my user application has it, and also the backend of the caching system has the file. And if I now want to retrieve the file or the data blob a second time, then I ask for the second time, and the NFS client does not need to retrieve it through the network, but can directly get it from the FS cache backend. So this transparently, as user and as a virtual file system, I do not know anything about it, as transparently just uses these cached files, which is very nice for us. But there's one challenge which has to be overcome, and this challenge is called, or we call it, cache thrashing. And this cache thrashing happens when the data that I need, the data that I want to load, was evicted from the cache before. So it's not there, even it would be nice to have it. In the first case, this can happen, of course, if somebody else evicts the data from the cache, so reads another file and then overwrites my cache, basically. And to overcome this problem of case 1, everybody, where it is possible, uses the same files and the same chunks in our system. So we have many different CMS analyses, and they all use the same data sets to maximally profit from each other's caches. And the second challenge is that you evict the data by yourself. So if, for example, there wouldn't be a problem with your data because you're loading the same data again, but you load it onto another worker, then of course the first worker, the cache from the first worker is evicted. And to overcome this, you not only need these caches, but you also need a consistent assignment between a job and the worker via an affine caching mechanism. And this is what I want to speak about now, how we did this. So this is really the connection between the storage and the worker. Now everything comes together because now we see that we always want to process the same data on the same worker. And how we do this is that we use a 64-dimensional representation in a virtual embedding space. And how we do this is that this embedding is constructed. For example, we use the string representation of one of our workers. In this case, it would be worker 01, and then with an SHA 512, we could transform this into 512 bits, and then each group of 8 bits we could interpret as an integer with a base 8. And for example, this representation here with an integer with base 8 would give an integer of 180. And we can go on and on and on, and this would then leave us with exactly 64 integers. And this is then our embedding in the hash space. So this is just a tuple, just a vector, basically, 64-dimensional. And we can do this not only for the workers. For the workers, we use the worker name, and we use something which is called ID, which is, you will see in a second what that means. But we also can do this for the job data. So for example, we can use this embed function I just explained you on the file name plus the event range we are currently looking at. And when we do this, we have depicted it here only 2-dimensional, such that visualization is easy. You can see that the workers, for example, here worker 2 and worker 1 are embedded in this 2-dimensional space, and also all the jobs are embedded. And already now you can see, okay, worker 1 is represented 2 times. And this is exactly what this ID is for. So in the wild, let's say, we have much more Dask jobs than we have workers, and to guarantee a more even distribution between the Dask jobs and the workers onto our 64-dimensional space, we place each worker multiple times. So in practice, we place it 10 times. And additionally, these workers have a property, and this property is a weight, which is in the order of the size of the worker. So we have large workers which can take more jobs, and we have small workers which can not take as many jobs. So these are our 2 tricks, which are right here. And then from this 64-dimensional representation, we can just take with the weighted Euclidean distance between the jobs, and then we can just make the assignment via the minimum distance, which, for example, for this point here, I can calculate the distances in this 2-dimensional space, and the minimum distance would be this. So I knew that this job should be matched to worker 2. And this is very nice now, because this results in an affine caching for on the one hand, because the file name and the event range I'm looking will always end up on the same worker node. So that's very nice. And also this is very graceful on failure. So for example, if one worker fails, or if 2 jobs fail or something like this, then, or if 1 worker fails or 2 workers fail, then the jobs will just gradually, gracefully go to different workers, but the whole system in itself will stay consistent and not be changed. So for our implementation, there are many alternatives. So for caching, there are many alternatives. For example, you have heard of Xcache, of course, which leverages this xroot D. The reason why we did not take this was that it does not give POSIX access. So we do not have like a real integration of it with, like we would have with a normal file system. Also, it would not be too easy with many users, because each one needed its credentials and so on. And there are a plethora of different distributed file systems. So these distributed file systems virtually span the file system over every storage architecture we have in our cluster. So the network attached storage on the one side, but also all the SSDs. And there are various different alternatives available, but none of them really fitted what we wanted to do. For example, we have Ceph here. Ceph is very nice, but Ceph does not handle changing files so well. So if one file is changed, then the assignment of the job to the worker does not go so well. For example, you have Extreme FS. This Extreme FS is also very nice, but does not support cache tiering. So the difference between you have the storage node and you have all the different SSDs. Then there's Cluster FS, which had the cache tiering implemented, but somehow removed it.
in the past. Then there's LHC, which is also nice, but not very graceful if parts of your storage fail, which is given in our case. Then we have MooseFS, which is also very nice, but has the downside for us that the caching is only based on the modification time. And of course, we do not want to modify our files every time, but the system should be stable from the beginning. And then also there's a very nice candidate which seems very promising, which is CVFS, but it's still very new, and it seemed to us that the documentation is not quite complete. So now that we have investigated and seen the alternatives, let me come to the benchmark and our results that we achieved on our cluster with our setup. Here for a benchmark task, we had a read-only task. So this would correspond, for example, to a pile-up counting or something like this, where you the most part of the workload is really opening the files and reading the files, and what you do with the files would not be too heavy. And we do this on 10 times. So we have, I told you in the beginning that we have the repeated evaluation of different tasks in our analysis chain for optimizing, for debugging, or really just for the pre-processing itself, looking again and again at the same columns from different tasks. And we're using 220 Dask workers in our case. The data we're using corresponds to a very actual Higgs pair production analysis, so contains about 1.4, 1.5 terabytes, which is about 10 to the power of 9 events. And we touch not only like you would do in the pileup count 2 columns, but we touch really 120 columns. So really a big portion of what you would use in your physics analysis at the end. On the files, we pre-process them to have them in a read-optimized compression state, where we use the Z standard algorithm with a level of 10. And now we want to look at the results. So here in the plot, you can see on the x-axis the different cycles that we read our data again and again, so submitting the same tasks again and again. And then we have 2 y-axes. On the left y-axis, we can see with the green bars the amount of data we read from our network attached file storage. And you can see that in the beginning, it is close to the 1,440 gigabytes that we have in the full data set. And on the right side, you can see the runtime in minutes of the whole reading, of the whole analysis, if you want. And you can see that from run 1 to run 2, there's a very nice decrease in runtime, so speed up of a factor of 6.3, because in run 2, of course, the read duration from the network attached file storage is not so high, because the caches are full and the workers do not need to load the data again. What you also see is that the cache performance is not 100% from the beginning, so not 100% from the cycle 2, and this really results in this gradual performance here. And this gradual performance is coming from the work stealing, as we call it. So in our case, if one of the workers is finished with all the work that was assigned to this worker, then we say, okay, it's nicer to destroy your own caches, but of course, calculate something. You do not have something to do right now, so you can steal jobs from different workers. And this concept is what we call work stealing, and this is then what you can see here in the gradual performance. And the second thing that we can see is that we reach with the runtime a lower bound of 6.3 times 2.4 speed up. And this is then the lower bound of the runtime, and this is really the CPU bound of the runtime. So in this case, we have solved our I/O bottleneck, because the analysis is CPU bound, again, what we wanted to achieve. So the impact, this was the impact on our benchmark. The impact on our analysis also very nice. Like I said before, we have a particular speed up for read-heavy preprocessors, so where you read again and again and again, and where your runtime is mainly driven by reading. And but also, of course, other tasks and other workloads profit from this caching mechanism. And for us, in our case, this really enables 3 run modes for the full analysis. So, for example, investigating 2016 data, which would be about 3 terabytes of RAM, 3 terabytes of data, and there we have 3 run modes. So for example, we have an explorative mode where we can, in 20 minutes, go without corrections and without systematic shifts and only simulations, but over the whole data set. So for example, I said in the beginning, if you want to see a plot or if the supervisor wants to see a plot of a master student or something like this, he or she can have it in 20 minutes, really including all the simulations from this particular year. Then we also have a quick mode, which is about 1 day, where we do not have the computation of very heavy systematic variations, for example, jet energy corrections, which takes about 6 hours. And then we have this full publication ready mode of analysis, which now takes about 20 hours, so much faster than we had before. So in summary, I showed you that we have implemented a very fast order of terabyte physics analysis on our small institute cluster. We have the columnar processing via NumPy and ORQuad mainly, and the job distribution is done via Dask through this map and reduce scheme. We have overcome our I/O bottleneck by this optimized storage distribution hardware on the hardware side through our cluster and our affine caching concept. And this enables us to have analysis runtimes in an explorative mode of about 20 minutes or a full analysis for the publication ready data analysis in about 20 hours. Thank you very much.
Okay, sorry, thanks very much, Dennis. Also apologies for being late, but that was a super nice talk, so thank you. And I see we already have multiple questions, so maybe let's first go to Alex.
Hi, yeah, thanks a lot for this talk. There's a lot of super interesting stuff in here, and I think I have more questions than we can fit in the time, so I'll be probably in contact via email. One question that I have that's sort of more general is, how do you think the system scales to larger clusters? Which is sort of, how much are you benefiting from the fact that you have only so many workers and you can sort of feasibly put everything into caches there? And if you had like thousands of workers, it's harder to hit those. So like, what do you think about scaling this to larger setups?
Yes, that's a very good question. So with this affine caching concept, you could also, of course, distribute this on a large cluster, right? And if you have 1,000 workers, for example, and they are all equipped with the with an SSD storage like they are on our small scale, I think this would make it not too different. Right? What is your thought about different distributions to different workers if the cluster gets smaller? If you say you have about, I don't know, 10,000 chunks or something, and you have 1,000 workers, then it's a very easy scheduling to schedule each 10 of the chunks on one of the workers.
Yeah, the thing I have in mind is sort of like, are you likely to have the right workers available to get a good assignment, which is potentially easier if there's only so many workers overall. That's sort of what I have in mind here.
Ah, okay, I got you. So, so in our case, this is a little bit synthetic of this side because we can book our whole cluster because it's our cluster. Of course, if you would go on an of a tier 2 size cluster, that's definitely a good point. That some of the machines would not be available to put the jobs on. Yeah.
yeah, I think as Alex said, we'll probably have more questions on email as well. But let's also go to Gordon next.
Excuse me, that was really a fantastic talk. Thanks for preparing it. So I guess I one technical question and one broader question. Just quick on the technical question. You talked about using you had a single machine or a very small number of machines which had GPUs to do the inference high speeds. What technique do you use to run your inference step? Do you just have a really small job in Laws/Luigi and it gets automatically routed, or do you use GPU as a service style interactions to make that work?
Mm-hmm. What we use there is the TensorFlow model server. And this just
okay.
Yeah, it's on the
GPU as a service.
Yeah,
perfect. So everybody can access it, and it's just a network
in the net within our network.
Pull the results. Yeah. Okay. And then the other question is the amount of work that it sounds like went into this is phenomenal. I mean, the work, for example, for understanding how best to do the histogram reduction step, where you're carefully monitoring your memory at the same time that you're accumulating the histograms and routing it. And there also, it sounds like you're pretty tightly integrated with modifications to, or loading modules at least, and configuring in the Linux kernel. Is this something that just you all as grad students and postdocs did? Is this something that was collectively done by, collectively done by a group with included sysadmin style people? I mean,
mm-hmm.
How did you accomplish it? It's insanely interesting and really a lot of work. It's pretty impressive.
Thank you very much. First, so we do this ourselves with this Whisper cluster that I showed you. We're about 7 people currently, and most of them do the analysis. And additionally, we have some part-time people there, but they're mostly there to write something from for the front end stuff and so on. So the sysadmin things we do all ourselves, from ordering the machine, so from collecting invoices in the beginning to buy the machines to finally set everything up with Ansible and then finally using it. And this also, of course, a nice privilege for us that we can really tune our cluster like we want.
Indeed. All right. I've got, like Alex, I feel like I have a lot more questions, but in the interest of everybody's time, again, fantastic talk and representing some really amazing work. Thank you.
Thanks.
Yeah, that's quite impressive. Okay, it looks like we have another question from Vincenzo, and then I saw a hand up from Nick, but it looked like that went down. But let's go to Vincenzo next.
Hi, Dennis. Let me also congratulate for this amazing talk. It was very, very nice. I had a question, a clarification regarding, so I think it's very clever the way that you solve this issue of cache eviction with the algorithm that you were describing, assigning always the same data to the same job or the other way around. But with respect of Dask, so let me understand, this works by computing where the Dask job or the Dask process, better yet, should be spawned, like before it starts, before the analysis starts. Then you SSH into an already running Condor job and you launch, like manually or with the script, you launch a Dask process that will then start running the task, the analysis, the application.
Yes, so for the detailed application, maybe Benjamin can say something to it because he has worked most of it. I think it's a central instance who spawns the Dask jobs.
Yeah, let me briefly go over it. So the HD Columnar jobs are directly submitted and start Dask workers that connect to the central Dask scheduler. So we basically quickly after startup have our Dask scheduler already filled with quite a number of workers waiting to basically accept jobs. And then we have modified part of the Dask mechanisms internally that distribute the incoming basically tasks, the Dask tasks to be worked on, and how they are assigned to the available worker pool. And this mechanism, there we have basically included the ability of this affine scheduling mechanics, and with that we can basically operate our cluster in an affine way. So it's basically standard Dask, how you would use it with HD Conda together with Dask job queue and a small modification on top of that.
Okay, well, that sounds amazing, because I mean the only thing that from the interface that you can't really do anything about is where the Dask processes are spawned. But then if you have this internal, I mean, I would go as far as asking you to publish or circulate this patch, maybe even upstream in Dask, because it sounds like a super cool feature that would be beneficial in this kind of workflows that we have.
That would certainly be a possibility.
Okay, it looks like we have another question from Nick.
I mean, to jump on that, I thought Dask had the ability to use the worker resources to label workers in such a way that the jobs would cluster to them.
Yes, resources. You can define something called resources, but we do not use resources per se. We basically use additionally information that we derive from the worker IP or basically a host name, and together with some information that we basically embed in the IDs of the tasks themselves, we can then basically in the Dask mechanism perform the affine matching between workers and jobs.
Okay. Yeah. No, I mean, like everyone else has said, this is really nice to see, and I've been wanting to see this for a really long time, basically ever since I first put nano events together with the column caching. I think we had talked long ago about using the column level caching, and in the end it looks like you ended up going with a file level caching.
It's more like an event level caching in the end then.
Yeah, and you know, because in principle, right, you could save some additional time by you know the uproot time spent parsing the files by doing the caching at the column level, like the column chunk level, and that might help, you know, get you a little bit faster in performance. It's actually one of the annoying things about Coffee right now is the time spent just in uproot, because well, root files are hard to parse.
Yeah, thank you very much.
So if Dennis has can hang on for I know we're already kind of at time, but if Dennis, if you have a little bit more time, it looks like we have 2 more questions. Is that okay?
Sure.
Okay, great. Can we go to Alex next?
Yeah, this is related actually to what Nick was just talking about. So looking at your like second to last slide, where you have the different setups, sort of explorative turnaround in 20 minutes and then going to 6 hours. In this setup where you have 20 minutes, do you know how long the individual sort of processing that just like processes a chunk of data takes? And is this 20 minutes now sort of like all just IO overhead? or is this like bound by something else? What I was surprised by is how much longer it becomes in your next stage, sort of going to 6 hours, which is like a factor of 20. And in that like connection, I was wondering, okay, are there sort of like known, understood things that are just complicated to calculate, and would it potentially make sense to save them if you need to run them again, if they're this CPU intensive at this stage? Because naively, like I always envisioned this system that sort of like everything is super fast and like you stay IO bound, but I guess looking at this here, it's like actual processing that's time that matters, right? Going beyond this sort of explorative stage.
Yes, I think so too. The factor of 20, which you have from the explorative to the quick mode, is really the multiplicity of these computation heavy, the additional variations you had.
Okay, and then so the amount of you say in the explorative it's only simulation, so like running over data then presumably is negligible because there you won't need to do all of the variations. So it's really just doing the systematics here, which does slow things down by quite a bit. Okay. And in both of these cases, how many sort of like units of work is it that like run in these 20 minutes? Do you know this number? I'm curious, just for reference, like to have a comparison to sort of other workflows here.
Yeah, so I would need to look this up afterwards.
Okay, I have some other questions. I'll write an email.
Maybe Benjamin knows. He just put off his microphone.
Yeah, so it's somewhere around 10,000. So I believe our most recent, quite a bit larger runs had about 40,000 chunks to process, and though we have recently added more data sets, so the numbers do not align with the times on this slide.
Okay,
But
so it's actually it's fairly short. So it's fairly short units of work then to be processed. So in that context, do you know whether the scheduling is efficient enough? As in, sort of, would potentially things be faster with larger units of work? Is there any appreciable amount of overhead just from scheduling everything and sort of orchestrating everything to run?
There is quite a bit of overhead from scheduling. So scheduling alone takes 1 to 2 minutes of full-time CPU load before basically Dask actually pushes out the jobs to the workers, though it's manageable. And we found that increasing, for example, the chunk size did not really help with the performance and only made basically memory limitations much worse.
Okay, that's super interesting. Thanks.
Okay, so I don't see any other hands raised. Although Vincenzo, you had one. Oh, I think Vincenzo left. Oh no, they're still here.
It's just a comment on a previous comment about the caching maybe in columns rather than full files, but it was just to understand whether with the current setup that was possible at all. I understand that you are not even using extruD for the caching, so. But then I also saw a comment in the chat by Jim, so maybe there's something that can be done even without in order to save only the columns. I also agree that that would be a good improvement over saving the file.
Yeah, and for the sake of the video, Jim had linked in the chat that Kurt Chunk can help. Okay, so it looks like that's it for questions. So let's thank
actually,
Dennis.
sorry. I just to follow up that I thought that the caching system was doing it per block, not per file. So while the block boundaries may not be on, column block boundaries or baskets or whatever, you still were effectively getting that kind of caching. Did I maybe misunderstand the caching system?
No, the caching is working basically on the level of events. because the job data embedding in this n-dimensional space is done by the file name and the event range that we are reading from the file.
Okay, I was thinking more about the low-level cache that was down on the NSF server, but you're talking about within the worker, which is different. Okay,
In the
perfect.
worker.
Yeah, that was my misunderstanding. Thanks. Sorry, Matthew. Go ahead. Finish up.
No worries, Gordon. Yeah. Oh, actually, so it looks like Peter also has a follow-up comment or question.
Yes, just a follow-up comment on this. I think you understood the caching initially correctly. So it's on the block level. And then we only cache what we read. So it's not the whole file, but only the columns we can read. But it's not cached in memory all the time. So just the columns we read are also cached on the SSDs, not the whole file.
But sorry,
cool. Thank you.
Format. Just sorry if I just want to understand, like how do you do this block block level caching on disk then? Is it within the FS cache library that this happens on the worker?
Yes, I think so. Maybe Benjamin can correct me if I say something wrong.
Yes, that happens as part of the FS cache system, and is basically entirely transparent. So basically, the parts of a file we read, we also get basically get cached in the process of reading them.
Okay, clear. Thanks a lot.
Okay, so it looks like we have exhausted the questions for today, but let's thank Dennis again for a super excellent talk. And yeah, we'll definitely be talking more over email. So thank you.
Thanks for having us.